What if I told you that some of the games you played as a kid, those easy ones you thought you were just messing around with or were better at with your hidden strategy, are actually disguised maths? Not easy maths either. Today we're looking at 3 games. Each one starts deceptively simple. Each one hides deeper mathematics than the last, ending with a problem that has stumped professional mathematicians, and it involves yummy chocolate. By the end, you'll see why these games are all connected by the same underlying idea. Perhaps the most simplest of all the games. It's 2 players, each can say up to 3 numbers or more. And if you say 21, you lose. That's it. Let's watch this game. Two questions, really quick. Who won? Is there a pattern in the numbers player 2 decided to stop on? Have a look, pause the video, I promise there is one. Player 2 won, but look at the numbers they stopped at each turn. 4, 8, 12, 16, and 20. All multiples of 4. That's not a coincidence. That is the whole strategy. Here's why it works. To win, we need to say 20. So let's work backwards. If our last turn was 16, our opponent can only reach 19, meaning we can always reply with 20. Let's use this logic as it applies backwards. We see that 12, 8, and 4 are all winning positions, all made by player 2, and all multiples of 4. The strategy is simple. Whatever your opponent says, you say just enough to bring the total to the next multiple of 4. Your turn always adds up to 4 together, so you stay in control the whole game. There is, however, one catch. To guarantee a win, you must be the second player, because the game starts at 0. The first player can never land on a multiple of 4. Against the perfect opponent, that disadvantage can never be recovered. Going second is the mathematical advantage here, and that's something we'll see come up again in the next game. Perhaps the most famous mathematical game ever invented. The rules are just as simple as before. You have 4 rows of matchsticks containing 1, 3, 5, and 7 matchsticks respectively. On your turn, you choose one pile and remove as many counters as you like, from 1 to the whole pile. As is the case with 21, whoever takes the last counter loses. That's it. Let's watch this game. Same question as before real quick. Who won? Can you spot the pattern? It's a lot trickier than before. Unlike the 21 game, the answer isn't obvious. No one took from the biggest pile each time. No one left equal piles each time. Sometimes one counter was taken, sometimes the whole pile. At first glance, it looks almost random. So let's simplify. Makes it easier to work with for us and our tired brains. If there was 1 row and 1 counter, whoever goes second wins. If there was 1 row, 2 counters, whoever goes first wins. If there was 1 row and 3 counters, whoever goes first wins again. Nothing interesting, right? So let's spice it up to 2 rows. 2 rows, 1 counter each, whoever goes first wins. Let's check 2-2. There are 3 possible moves here. Who lose immediately. The only promising one is to leave 1-2, which we already know is winning for them. Now think about 3-3. Is it the same idea as 2-2? Pause the video, have a think. Yeah, it is, because they're both equal rows and equal columns. So does that mean if it is equal and you start your turn, you lose? Maybe. How about another row? Let's look at 1-1-1. If we, player 1, go first, then it's back to 1-1. And as proved earlier, it's a win for player 2, as they have seen it this sit up on their turn. So it's a loss for us. So equal piles clearly aren't the trick. We found a pattern, but not the pattern. Maybe we've been looking at the game the wrong way. Instead of thinking about the counters themselves, let's think about how the numbers are actually written. How can we write out our numbers differently? Binary. It's just another way of writing numbers. So before we look at XOR, let's write our pile sizes in binary. Then 1 is equal to 001, 3 is equal to 011, 5 is equal to 101, and 7 is equal to 1, 1, 1. XOR stands for exclusive OR, meaning look at one column at a time. If that column contains an even number of 1s, write down a 0. If it contains an odd number of 1s, write down a 1. Let's do the XOR operation on 1, 3, 5, and 7. The XOR operation is called the nim sum of the current position. Here's the amazing part. Every losing position we've found so far has one thing in common. Their nim sum is 0. 1, 1, 2, 2, 3, 3. Even our starting position, 1, 3, 5, 7, is 0. This isn't a coincidence, it's the entire strategy. Just like we had with handing our opponents multiples of 4 in the 21 games, here we are handing our opponents a position with a nim sum of 0. Whatever they do, we must break it. Our job every turn is to put it back to 0. The only exception is at the end of the game, when if there is an opportunity to leave one counter and make your opponent take the last one so you win, you must take it. Apart from that, the game is beautiful. Always leave your opponent a nim sum of 0 to guarantee a win.
So far, every game we've seen has had some elegant mathematical strategy to win. For the 21 game, it chose multiples of 4 as its winning strategy. The nim game had the XOR operation / nim sum. Surely, every game has a pattern hiding underneath it, right? Well, let me introduce my favourite game, Chomp. Chomp works very similarly to how the others have worked. Imagine a chocolate bar, assume your arch nemesis, player 2, poisoning the bottom left square. So don't eat the poisoned square, or you can't do more maths. And on your turn, you choose a square, and you eat everything above and to the right of that square. If we copy the next steps of what we have done before, what do you think we should do? Is it different cases? Is it starting second? Is it looking for number patterns? Is it combining previous arguments? Well, it's kind of all of them. Let's make it smaller and simplify it into something easier to imagine. We'll use a cross by height for notation. If it's a 1 by 1, it's a clear loss. 2 by 1, winning. Eat the right square, the opponent dies. Does it also work for 1 by 2? 3 by 1, winning, because you can eat the square 1 to the right of the poisoned square. So think for a second. Can't you just eat the square 1 up or to the right of the poisonous square? Have a think. Yes you can. This means that a winning position for player 1 is 1 by n and n by 1, where n is any counting number, also known as a natural number. Let's do what we did for nim and make a table. What about squares? Who wins? 1 by 1, we already checked, we're done. 2 by 2, there are 3 sensible moves. 2 lose immediately, the third creates an L shape, which is winning, as it forces player 2 to eat one of the squares and leave us with a line. 3 by 3 is the same thing. We can just keep getting into an L shape, which we win, and any other move is bad, right? Therefore, we can add 2 more things to our table. An L shape, it's a losing position for us to receive, and an n by n square, as it's a winning position for us to receive. So maybe that's the strategy. But what about rectangles? We know that we lose for 1 by 2 and 2 by 1. But what about 3 by 2? We can assume it's just the same as 2 by 3, just rotated. 3 by 2, it's like a square, kinda. We can make it into funky shapes, but it ends up either as a line, or an L shape, or a square, all of which we know how to win. This means we can win in any form of the shape, right? Can you prove this? You can, but it's hard to think about. Now suppose for a moment that player 2 has a perfect strategy. Player 1 makes any opening move. From then on, they simply pretend to be player 2, following that perfect strategy wherever possible. If the strategy ever asks for them to make a move that's already been eaten, they simply choose another legal move instead. Eating more chocolate can never create extra legal moves for your opponent. It only removes them. So player 1 can never be worse off for having made that extra first move. But that means player 1 has stolen player 2's supposedly perfect strategy. That's impossible. Therefore, player 2 cannot have a winning strategy, so player 1 must. Unlike all our other games, going second actually means you are losing for any position at any size of chocolate bar, as player 1 is always in a winning position. This type of proof is called a proof by contradiction. Assume the opposite is true, show it's impossible, and the original statement must be true. This idea is what makes Chomp so fascinating. We've proved the first player has a winning strategy no matter the board, without ever finding what that strategy is. But for an arbitrary board of any size, we still don't know the simple formula that tells us the perfect first move, despite knowing there is one. So, in conclusion, we've looked at the 21 game, Nim, and Chomp, and how mathematics can be hidden in surprising ways inside games that seem incredibly simple. Throughout this video, you probably thought you were just learning 3 games, but without realising it, you've also learned how mathematicians think, working backwards, simplifying difficult problems, searching for patterns, and proving ideas. Along the way, you've explored modular arithmetic, binary, XOR, combinatorial game theory, and mathematical proof. The games may have been simple, but the math behind them certainly wasn't. Hopefully, the next time you cross a puzzle or a game, you look at it a little differently, and start searching for the mathematics hidden inside. Thank you for watching.